The goal of this video is to explain how to code a center mass calculation. So give me just a second. All right, let me get my screen up here. Whoops, wrong one. Let me do a screen share here. Sorry about that. There we go. Okay, so hopefully I'll be able to give you a link to this either in Canvas or maybe as a comment in the YouTube video itself eventually, if I remember. But so hopefully you've got some code here. Let's just walk through this to kind of see what we've got. I'm going to specify the rod length. Let's make that 5.0. I'm going to specify a minimum position here. So this is going to be the left end of the rod eventually. And this will be the right end of the rod, basically. So I'm going to take that minimum value and add to it a length. More on why I'm doing it this way instead of just saying, why not just say rod length? Well, we'll get into that later. Mu is going to be the mass density. So let's say we have a mass density and we don't know the mass. Why do it this way? Well, this will help understand non-uniform problems. So, okay. And so in this case, let's start with, I think I wanted to start with n equals, let's just start with n equals 5 for right now. We could always change it up later. And so it's nice to start with the small number because when you're coding these things, then you can actually kind of think it through and count things without having to count to 100 or 200. And then dx, this is going to be the length of one segment of the rod. So think about it. We already know the rod length. You could just say, well, if the rod length's 5 and I know I'm going to cut it into 5 sections, each section should be 1 unit long. Sure, but that's not a good way to code it, right? We want to use these parameters like this. And I think that's it. The idea now is, what if I choose a different rod length or a different number of segments I need to use? I don't have to redo this part. This is done forever. So this is not required, but it's advisable, especially considering I know what the quiz questions I'm going to ask are. So let's keep going here. Now, this is going to draw something, and this is going to draw something. So why don't I comment out these, control slash there or whatever, backslash. Okay, and so just, I don't know if you could see, but there's a faint gray cylinder there that's indicating where the rod is. Now you might be saying, why didn't I draw that brighter? Okay, I could actually change the brightness here by changing the opacity, say to 35, but I actually want that to be very dark in the background. So it just kind of helps me identify approximately where this rod is supposed to be. Now we're going to build this out of other chunks in a minute. And so I don't want that to be in the foreground. I just kind of want that to be a visual guide for where this thing should be drawn. All right. And notice right now, if I do this, if I change this X minimum to 2, all I did was change this one line of the code. And notice that will shift it over and I didn't have to recompute everything. What if I change the number of, well, yeah, okay, we haven't done anything else yet. So let's go back to 0 here before I forget. All right, next. Let's say we want to create a numerator. So now what I'm going to do, the numerator in the center of mass equation should be a vector. All right. And the denominator is just going to be a constant, a scalar. So that's initializing those two things. Oops. There we go. Sorry, I like to keep my spaces together. And then right here, what else do I have here? Oh, I'm going to create a list. This is something that's new that we haven't done before. So notice the type of bracket I used, not using parentheses. So that's a list. And then over here, I want to create an increment that I could use in my loop. All right, and I think we've got everything there. All right. And so if you're wondering what I'm trying to do here, let me remind you of the center of mass formula. I know that the x coordinate of the center of mass is equal to, in general, in calculus, we say this is the equal to the integral of x dm all over the integral of dm. Well, in this calculation, we're going to basically change back to the summation notation. So in this case, we could say this is equal to the sum of x sub I times mass sub I, right? From I equals 1 to n. And all that is divided by the total mass. Well, the total mass, that's just the sum from I equals 1 to n of m sub I. Now, we want to actually upgrade this to a vector because we're in 3D code. So we could say the r vector of the center of mass would equal, and just I'm going to leave off the summation, all of the bells and whistles for a second. So this would be the vector times each little chunk of mass over the total mass. And notice the numerator is indeed a vector and the denominator is going to be a scalar. That's why right here, the numerator is a vector and the denominator is a scalar. Now, before I forget, I'm going to actually, whoops, let me see if I can make this a little bit bigger for you so you could see better. I apologize, and we'll catch up on that code in case there's anything you missed. So getting back to my annotations here, that's what's, let me get rid of these arrows here. All right, and so that's what I'm doing. I'm setting up the numerator and the denominator for the center of mass formulas, and a list will explain why I'm doing that later. Now, I want to warn you of something. When you see these in calculus class, we usually go from 1 to n. However, in Python, notice what I did here. Why did I do this? We generally speaking start at 0 because I don't want to go into why right now, but basically the first element in a list is usually called the 0th element. And then the second one is called the first, etc. So instead of going from 1 to n, we're actually going to go from I equals 0 to n minus 1. And so in our while loop equation, we don't want to say I less than or equals n. We want to do I less than n. That way we go from 0 up to n minus 1, but don't include n itself. I think that's good enough on that. All right, so now I could go ahead and back these out. Now I'm going to show you how to do this with the while loop, and then later I could show you how to do it with a for loop. So in this case, let me just copy some code so I'm a little bit faster here. I apologize for doing this to you. Let me copy this and put this in here. Okay, so what I'm going to do is inside of the while loop, I'm going to draw a ball. Okay, the ball's position, I'm going to put wherever the rod visual guide's position is. Remember, the visual guide was that little picture we drew. So this would say, go to wherever that visual guide started. In this case, that will happen to be the left end of the rod, and then add to it this complicated looking vector. Well, let's break this down. Okay, dx, that is going to be a small distance in the x direction that we calculated out earlier. If you remember, dx was something like the rod's length. I'm just going to call that L for right now. Okay. Hold on. So the rod's length, excuse me, divided by the number. Okay. So, and again, for us, let's say we had 5 and n was also equal to 5. So notice dx is equal to 1 in our case. Okay. We're starting here at I equals 0. That means this number right now is 0. I'm going to scoot over a unit of 1 times 0. Well, that's nothing. Plus another half, right? 1 over 2. So the idea here is this first ball will actually be drawn a half unit over. Why am I doing that? Because a ball's position is actually at the center of the ball. So if I have my rod visual guide here, right, this might be the visual guide. Okay, there's my visual guide. This is the position of the visual guide. If I draw my ball there, it's actually centered on the left end. Whereas if I use, excuse me, just get a different color here. If I add half a unit, that'll draw it right here. So the left side of the first sphere I draw will actually be at the left end of the rod. So that's why I'm having to do this little bit of finagling here. And there'll be some questions in the quiz, and you could see what happens if we don't do that, and you could see if this causes errors or not. So that'll be questions in the quiz, is what happens if we just get rid of this term, or what happens if we do the less than equals? Does it make a big difference or not? We'll address that in the quiz. Okay, so all right. And now this just makes the ball semi-transparent. So opacity ranges from 0, which is invisible, to 1, which is opaque. And so, all right. And notice here, this is just setting the size of the ball so it fits inside the visual guide. Before we go on, let's run the code and see what it looks like. This is good practice, and make sure I didn't make a typo when I was clicking around and doing all this stuff. This happens to me a lot with GlowScript lately. Notice it says modified, and it's not letting me run my code. What do? I'm going to hit Control A, Control C. Now I've copied this entire code. I'm going to hit refresh. Okay, when I do that, I'm going to click in to edit the program again, and I may have lost some stuff. It looks like I may have gotten it all, but just in case, I'm going to again hit Control A and Control V and paste it in. So that means that makes sure I didn't miss some typing or something. Okay, so now I'm going to run this program and see. Oh, notice it only drew one ball. All right, so let's go down there. I forgot we should probably stick inside of here. So I'm going to do some coding in a minute, and let's see. Let's just stick this down here somewhere. How about right here? Whoops, how about right here? We'll say I plus equals 1. So that's just going to increment the I value, and let's run it again and see what happens. Hopefully that fixes this. There we go. And notice this looks about right. If I could make this bigger and zoom in, notice the balls happen to fit perfectly inside of there. Now you could ask, what if we do even or odd numbers? Well, we could just run that, or I could let you figure that out on your own. But since it's so quick, I'm going to hit Control 1 to run. Notice the balls have to overlap a little bit this time. So, all right. So things look slightly different with even and odd numbers in this type of code. Whatever. Let's go back to our standard code, 5.0. All right. So now let's go down into here. Let's say I want to determine the mass of each chunk here. So, right, the balls are like little chunks that are building up the rod. So let's figure out that. Let's define a new attribute, ball.dm. Okay. And let me make sure I'm doing the same way I wanted to do it before. Equals mu star dx. Now, what the heck is mu? Did I do that up here? Yes, I did. I defined the mass density. Obviously, if you knew an object's mass and its length, you could actually do a little calculation in line 6. You could just say mu equals m divided by L. So that's how you could generalize this if you knew the mass. But all right, so there we go. We've got this. Now that's not going to draw anything, so we don't need to do anything. This is a subtle little line of code here. I want to do, let me make sure I write it right. Rod was the name of my list. So right here in line 24, I created a list. Okay. And just in case you can't see this, let me get a little bigger again. Rod is the name of my list. So I want to do rod.append. And then I'm going to add the ball into the list. So append, this line of code basically says, okay, you had a list that was empty named rod. I want to add this ball into the list named rod. So what will happen is this object with all of its properties, all of this junk is going to get dumped into here. And if I ever want to refer to that, I could actually just type rod 0. So at this point, remember, I is equal to 0. The 0th element of a list, in particular, this particular list, is now this ball. So if I could do rod0.pause, would actually talk about, it'd say, okay, go to the 0th element of the list. Well, that's this particular ball with all these different parameters. Go into the position, and I could do this. Or I could even do this, rod.pause.x. So, oh my gosh. Okay, fine. This would get the x coordinate of the position of the object that is the 0th element in this, which is the ball. Holy cow. So this is very useful later on. Okay, so let's take that out for right now. Now, all right. In this case, oops, there we go. So now what I want to do is I actually want to do that sum, and I'll write that up here again. Sorry if this video is long, but I think it's worth taking the time. So remember, we're doing basically a sum of R sub I, M sub I, all over the sum of M sub I. And we're going from 0 to N on both of these. Oh, sorry, 0 to N minus 1. Excuse me, 0 to N minus 1. Right? We go from 1 to N or 0 to N minus 1. I apologize. Okay, so I'm just going to keep that handy there while I type this right. So the numerator should equal, check this out, rod I dot pause times rod I, whoops, wrong bracket, I dot dm. Now think about this. This is not quite right yet, but it's close. This is going to go in, and right now I is still equal to 0 right now. We haven't even incremented yet, right? We haven't gotten down here to where we added. So I is still 0. We come in here, I is equal to 0. We do all this stuff. We add it to there. Now it's going to go in. It's going to get the 0th position vector. Got it. That's a vector. It's going to multiply by the 0th mass. Got it. Now what we want to do is a sum. So instead, right, if we go down here and we keep going, I is going to add to this. And then I would be 1. 1 is still less than 5. N is equal to 5. So we would come in and do it again, but then the numerator would get overwritten. So we actually want to do a plus equals here, right? And so what's going to happen is each time this increments, we're going to get a second, a third, fourth, and fifth sphere inside of here and mass, and this will add them all up. So that's pretty cool. And similarly, we could do the denominator, and that's going to equal just the rod I dot dm. Okay, and so let me make sure here. I didn't make any mistakes that I'm forgetting here. All right, so that looks pretty good. All right, and so now let me clear my annotations. And let's see, notice up here, this is, I want this video done. Sorry, it's long. I don't care. I've been working my butt off, so I got to get this over with. So I'm just going to deal with this. Again, I'm copying everything, and I'm going to hit refresh, and then I'm going to have to lose all that code. I don't know why it's happening so much during this video, but so see all that code's missing. So I'm going to hit Control A, Control V. All right, I got it back. So now I've typed a lot. Let's run it and make sure I don't have a bug. There we go. All right. And so, well, it compiled. So that's good. So that means it's doing this thing. So finally, we're now actually ready to compute the center of the mass. And so this is going to look a little bit crazy. So I'm actually going to dump a bunch of stuff on here. And what did I want to do it for? Okay. So let's just do a dump of all this and get this over with. All right. So now in this case, when we look at this one, okay, this is the total mass. Remember, the denominator should be, oh, wait, I screwed up in the denominator in line 48. I didn't do a sum. That will do a sum, right? I just caught it in the nick of time. So remember, plus equals changes this from just one value to adding up all the different values. Apologize there. So now the denominator will be the total mass. Down here, let's look at this. All right. So in this case, the theoretical total mass should be the mass density times the rod length. Got it. And now I'm going to calculate the percent difference. All right. So I'm doing experiment minus theory over theory times 100%. The experiment in this case, in my mind, is the code, right? That's the thing we're testing today. And then I'm going to print out the percent difference. Now, how do I get the center of mass itself? Well, that's just the numerator over the denominator, right? Now, what I'm going to do here is this is just drawing an indicator to show me where the center of mass is. So that's just something pretty to show me the location of it. And that's just setting the radius to the same size as everything else. And then I'm going to check what the theoretical center of mass should be. Think, it should be at the center of the rod. In this case, our rod's position in the x direction right there, plus half the length, should be at the center of the rod. And then I do a percent difference. So I'm going to crank this out and let's run this and see what happens. Hopefully I didn't make a typo. We see the balls being drawn. The center of mass right in the middle of the rod there. Let's zoom in. All right, we can see it's right in the middle there. Okay, and notice in this case, I have the total mass is 5, which is what we expect if the mass density is 1 and the length is 5. Okay, and the code was executing this perfectly in this case. And the center of mass is at the correct position, and that's computed correctly. If we change this number to say, if we did say 5.324 and maybe did say 7 of these, we might not get exactly the right answer, but let's find out. I suppose I should have sped up the rate at this point. So you may want to do that for subsequent ones. So notice we get a small numerical defect, and we've got an E minus 14. That sounds like a double error, but yeah, you could talk about floating point numbers versus double floats or whatever. And you can worry about that later. But so we see it's basically 0. Because it's something times 10 to the minus 14th. So this is looking pretty good. And you could debate whether even or odd numbers changes this, and you could try playing around with it. So try using 6 or whatever. But so we see that it's not always going to be a perfect calculation. I'm just going to set this back before I forget. So we had 5 and 5. So that's the basics. And from here, if you wanted to stop watching this video and start getting to work on your Canvas quiz, you could. But I'm going to show 2 extra steps, and I'm just going to do it in this one video because I can't stand doing this all day. So there's 2 things I want to talk about. One is, boy, we're doing this percent difference a lot. It might be nice to have a function. You could actually learn how to create a function, and I actually created one over here. So let me grab this one here. So let me show you this. This is kind of a cool trick. Notice we keep doing the percent difference over and over again. And our percent difference is always going to be experiment minus theory divided by theory times 100%. So this defines a percent difference function. Okay? And so the idea is, once you define this function, we could use this function over and over again to do all of our percent differences instead of having to do that one line of code over and over and over. And just to show you this works, let's just write this. Let's say pdiff comx2, right? The second version of it should equal the pdiff function of, let's see, the experiment was center of mass dot x. That's the x coordinate of the center of mass. What was that? Remember, it goes out and says x coordinate of center of mass. Well, center of mass was defined as, oh, that's right, numerator over denominator. So that's fine. That's the experiment. Our theory was, we already calculated that. I think it was CMOX. Okay, there's something like that. Sorry, it's a little bit. Let me hit return here so I can see that. Yes, so it's getting this value, all right? And so if I run this again, and let's do this, let's speed up the rate so we don't have to keep watching this over and over. All right, you could just take the rate statement out at this point and it'll go super fast. So there we go. And notice, oh, I forgot to print it, didn't I? Oh, whoops. Oh my gosh, what's happening here? Let's reload. Oh my gosh, come on. There we go. So let's pick a weird number. I think we said 5.32145 or whatever. And we said, let's use 7 here. And then let's go down to here. And I better print this. So I apologize. I forgot to do that. All right. So when we run this one, hopefully we get 2% differences down there. Oh, all right. So I'm doing something a little bit funky here. All right. Apologies. Oh, let's see. How about I just do this? There we go. All right. So sorry about that. My apologies. All right. And okay, so we're getting 2 zeros here, but we can see now this is computed correctly. Obviously, we might need to mess around with this to show that it's really working, but I hope you could believe me that it's actually working. So that's a trick to do a function to help you. Obviously, once you create that function, you could call it all the time, and we could have used it over and over and over anytime you need a percent difference. And you could imagine there's many different possibilities you may want to do this. The other thing that I want to do, and just to speed this up, I'm going to show you a different version of this code where I used a while loop. Let me see if I've got it here. Okay, so let's go into here. This is a while loop. So wait, we just did a while loop. I want to do a for loop. Excuse me. Sorry about that. For loop. There it is. So the same code here. Very similar. Very similar. But down to here, this is a different statement. So this is one possible way to do it other than a while loop. There are many others you could think of. But notice what this does. This says for x. Now, I hope you've noticed nowhere in this code up above have I defined what x is, right? Rod length, x min, x max, but I didn't actually define x anywhere. So x is a new parameter that for the first time is mentioned in this for loop. So it says for x, so for some random new quantity in this range, in a range of values. It goes from the minimum value to the maximum value in increments of dx. So that's how this function for x in a range works. All right, so in this case, notice what it will do. First, it draws the ball. And now inside of here, we could actually change this from this ugly thing to x plus dx over 2. And so in this case, we no longer have that big ugly thing with the letter I in it. We can actually get rid of that and change that to this. And then from here, the rest of the code, I still need the increment I, and I still need to increase it because I was using that to do my sum. So it's not like you can get rid of the increment I in this particular code. But if you weren't having to do a sum, you could actually get rid of the increment I as well, right? So the for loop, what this does is it comes in here and it says, create this parameter x, start at x minimum, go through this code. Once you finish, go to x minimum plus dx, do it again. Then once it finishes again, go to x minimum plus 2 dx, and just keep doing this over and over and over until you reach x max. Be careful. If you hit X max exactly, it will not do it, right? It will not execute. So yeah, this does a strict less than, I think. So anyways, let's run this one and make sure I didn't screw up. And so, oh, I did 10 spheres. Let's do 5 just so you could see. All right, so when we run this program with 5, we see it does draw the correct number of balls, right? 5, and it gets the same outputs. So that's 2 alternatives you could use. Functions for the percent difference could be a very handy trick to learn. And you could also use a for loop. Let's stop the stream there. Whoops.